Hi, my name is Sonny Castro, and in this video, we're going to be discussing the final project for ISM 6136 data mining. Data set that I chose for this project is the lower back pain symptoms data set. Problem statement: low back pain is a problem which affects many. The symptoms for lower back pain vary greatly among patients. Medical personnel need a way to effectively diagnose lower back problems to effectively prescribe treatments. Doctors, medical, and health technicians need an objective, widely accepted, and easy to explain way to determine which treatments a patient suffering from low back pain might require. One way to reach a better diagnosis is to determine early on if a patient has what could be considered a normal or abnormal spine. And the task for this project is to quickly generate a prioritized list of patients with a high probability of having a normal spine. Let's go through an overview of the data. The data has 310 observations, 13 attributes, which are divided into 12 numeric predictors and one binary classification attribute, which we use as the target variable, and no demographics. The numeric predictors consist of lower back spine-related measurements. These are measured in millimeters and angles in some cases. The single binary attribute is whether a spine is classified as abnormal, abnormal, or normal based on the 12 numeric predictors. This binary attribute was used as a target variable. So 285 observations were used for training and evaluation, and 25 observations were used as a simulation for new data for scoring. So these 25 observations from the original 310 were used to simulate new patients coming into the system. Looking at the variables by words, we can see here that degree of spondylolisthesis, or DS, is the variable with the most words, followed by pelvic incidence and pelvic radius. And I will explain a little bit more about what those variables are. So the first graphic here, we see what we mean by DS, and it's basically this degree of slippage in this the last disc of the vertebra. And you can see here the distribution. Pelvic incidence is this angle, so that's what we're measuring, and so this is measured in degrees. And pelvic radius is the measurement from this part of the hip to this vertebra over here, and that's measured in millimeters. So these are all measurements of the spine, the lower spine. In here, you can see the distribution of these three variables. PI and PR, you can see that they are fairly normally distributed, while DS is not. And for this reason, I conducted a transformation using log 10 to normalize the distribution. Just real quick before we go into the system, on the methodology was to explore the data, which you saw that I did in the prior slide, a little bit of that. Partition the data 7 to 30, analyze using, first part is analyzed using non-parametric models. Decision tree, an interactive decision tree. This is an automatic decision tree, and gradient boosting. Then transform the variables to get them ready for regression analysis. Conduct variable selection to do the neural network and an automated neural network. And then compare all 6 models to determine a champion. Score new data using a champion model, the champion model, and produce an output, which is the list of patients sorted by probability of having a normal spine. So it's a fairly straightforward method. The results, spoiler alert, the winner was the gradient boosting model. That was the champion. It showed the best predictive results. And I used misclassification rate as a selection statistic for model comparison. And Gradient boosting produces a prediction model in the form of an ensemble of weak prediction models, in this case decision trees, and here's a graphical representation of that process. The results of scoring contain a sorted list of scored patients ranked by how likely they are to have normal spine, and here's a screen capture of what the results look like, ranked by the probability that a patient has a normal spine, all the way to patient 298, which is very improbable that this patient has a normal spine. So this patient definitely has or there's a high probability that this patient has an abnormal spine. Before we go into the implications, let's go into the actual system. And here you can see, just real quick, this is the data set of 285 observations. This is what I used to explore the data and to determine which variables had skewed distributions, which turned out that DS was the only variable that had a skewed distribution out of all. The data partition, I already discussed that I use a 70-30 split, 70 for training and 30 for validation. I didn't really have to replace any values. This was very clean, but I double check using that replacement. And then here you can see the decision tree, the interactive decision tree. With all the different nodes. I believe this has 21 nodes in total. And then I transform the variables. I transform one variable, the DS variable, the degree of spondylolisthesis, using log 10 before performing a regression analysis. And then variable selection before performing the two neural network models. In the model comparison, we can see here the results. You can see here that the gradient boosting model was the one that was that showed the most predictive power, with a 0.7 misclassification rate. And you can see here in the graphic how it performed, followed by the autoneural network and the neural network, followed closely by those two models. The score, and then the SAS code. I use a SAS code node to generate the results, and they are sorted by the patient that has the most likelihood of having a normal spine, and we can establish a cutoff value for this, maybe 0.60, maybe 0.5, but we know that patient 295 has a relatively normal spine, or a high probability of having a normal spine, while patient 298, there's a high probability that this patient has an abnormal spine, and then followed by 303. So these patients in the bottom, they have high probability of having an abnormal spine, and a doctor or a hospital or anybody treating these patients can use this as part of their assessment for diagnosing these patients. All right, to finish off, let's look at the implications. This example can be applied to other cases where body measurements are used for initial diagnosis of conditions, and a similar method can be used to rapidly diagnose group of patients using human measurements as the data, as the variables. And on the larger sense, we can look at the human body as a data source. Our bodies are constantly generating data, and this data can be aggregated to monitor and make assessments about our health, early detection of heart conditions, diabetes, etc. This concludes this video. Thank you and goodbye.